So today we want to look at some ways to graph a quadratic function without using a full-blown table of values. And hopefully before watching this video you've had a chance to do a bit of exploration with quadratic functions, where we begin with a basic parabola y equals x squared as you see it here. And then what we're going to do is we're going to change some of the parameters or numbers in various parts of the equation. So over here, the first thing I'm going to do is I'm going to change the value of a. So instead of having 1 times x squared, what would happen if I had 2 times x squared or 3 times x squared, etc., etc. So as I do that, I'll notice that if I change it to 2, the graph is getting skinnier. And the higher a gets, the skinnier it gets. Let's just go back towards an a value of 1, where it's back to the regular one. If I go less than that, the graph gets wider. All of the y values are being multiplied by the value of a, causing them to go above or below where they were previously, which is then causing the graph to stretch or compress. If I go to a negative value for a, I'll notice that the graph is opening downwards. It's a reflection across the x-axis, as you can think of it. And again, the same kind of wideness, narrowness issue happens as I change the value of a. So what we're seeing by exploring with our parabola is multiplying by a does two things. First of all, if a is positive, the parabola opens up. If a is negative, the parabola opens down. And then if the value of a is larger than 1, and in fact if it's negative, the same thing happens if we think of the positive of that negative. So I'm going to say absolute value, which just means the positive of whatever the a value is. If that number is greater than 1, we get a vertical stretch. The graph stretches vertically by a times. If the value of a is less than 1, but bigger than 0, it can't be 0, otherwise it reduces to a linear function, we get a vertical compression by a times. Okay, so multiplying the function by a constant a changes whether it opens up or down, and it changes the wideness or skinniness of the graph. Alright, the next parameter we're going to influence is a number added or subtracted to x on inside of the brackets, which I'm calling p. In this animation they're calling it b. So let's take b and move it to be a more positive value. Positive 1, let's go up to b equals 2. Now you'll notice what's happened is the graph has shifted 2 units to the right, and my equation is x minus 2. You might be wondering, we're saying b is 2. Remember the minus is there, so if you just take the b away and slot the 2 in, you get x minus 2. So when we see x minus 2 squared, we're thinking of the b value just being that number. If we go backwards to a negative b value, negative 3, alright, so we're slotting negative 3 into here. X minus negative 3 makes it x plus 3 as you see it here. And what has that done? It shifted the graph 3 units to the left. So as you play around with b, you can see what it's doing is shifting the graph, translating the graph left and right. It's keeping it the same shape, it's keeping it congruent to what the original one was, but it's shifting it left and right. Alright, so p, if greater than 0, translates the graph p units to the right. And just to make this clear, because this is a little bit confusing sometimes for people, if I write x minus 2 squared, what I'm saying is that p is 2, which is a shift 2 to the right. If p is negative, then I'm translating the graph p units left. And again, just to make that clear, if I have y equals x plus 1 squared, because my standard way of writing this is set up as x minus, I have to think of this as x minus negative 1 squared. and therefore P is -1, which is to the left. The final influence we want to look at is adding a constant Q to the end of the equation. And in my applet, that's represented by C. So let's go to positive values of C. And what you'll see is the graph is translating vertically up and down. If I go up to a C value of 3, x squared plus 3, my graph has shifted upwards 3 units. If I go to a negative value, -1 let's say, if the constant is -1 at the end, my graph vertically translates 1 unit downwards. So if Q is a positive number, graph translates up Q units. If Q is negative, the graph translates down Q units. So we can summarize these transformations into a standard form equation of the quadratic function. If you have y equals x squared, multiplying x squared by a will do a vertical stretch or compression as well as open the graph up and down. If you add or subtract into the x, you will do a horizontal translation, left or right. And if you add a constant onto the end, q, that will vertically translate the graph up or down. Furthermore, since the vertex of x squared was 0, 0, then the vertex of the standard form, if it's been shifted p units horizontally and q units vertically, would become p comma q. A is the vertical stretch, compression, direction of opening, and P and Q are the horizontal and vertical translations. So if I were to look at my animation and take my A value and change it to 2, my original graph x squared vertically stretches, because A is positive, by a factor of 2, which means each of the y values, see the original y value here of 1, it goes up twice as far to 2. The y value here of 4 goes up twice as far to 8. It's vertically expanded, stretched. Think of it stretched vertically this way by a factor of 2. If I change my b to -3, x minus -3 shows up as x plus 3. I've shifted my graph 3 units to the left. And if I change c, let's say, to -1, I'm vertically translating my graph 1 unit down. Alright, now what you're going to need to do is take what we just talked about and be able to graph a parabola fairly accurately on paper. So I'm going to graph this parabola equation that I have here with 3 points of accuracy and indicate the asked for properties. So I'm just going to write my equation down below so it's a bit bigger. My equation, you'll notice, is given in standard form, which means in the form of what we just talked about. A number multiplied to the x part. X has something added or subtracted to it on the inside, and there's a constant q on the outside. And we know what each of A, P, and Q does. Okay, so A is 2, which means the graph is going to open up because we have a positive value of A. It's going to be narrower than a normal parabola because A is more than 1. P is -1 because we think of it as x minus -1, which means we're going to translate the graph 1 to the left. And Q is -3, which means we're translating the graph 3 down. And what the translation information gives us is the vertex. We're not vertexed at 0, 0. We are 1 unit left and 3 units down right there. So my vertex is -1, -3, which, as we indicated before, is the values of the P and Q parameter. The axis of symmetry runs through the vertex vertically. So the axis of symmetry is this reflection line. So we know that that's x equals -1. Now we want points of accuracy. We know the graph opens up. We know it's narrower than normal. So what I like to do is just take a value of x 1 or 2 units over from the vertex. So from -1, I'm going to go over to x equals 0. And I'm going to plug x equals 0 into the equation. Alright, so I'm just going to talk this out. X equals 0, so 0 plus 1 is 1, squared is 1. 2 times 1 is 2. 2 minus 3 is -1. So I have a point of accuracy there, which conveniently turns out to be the y-intercept, which I was asked for, so that's -1. And because of symmetry, I know that if this point is on the graph, then there's a point on the other side of the axis of symmetry, like so. And then I can complete my sketch. The minimum value of the graph, it's a minimum because the graph opens up. The minimum value is the y value. There's a minimum value of -3. The domain of a parabola, of a quadratic function, is all reals. And the range, as we can see, is a low y value of -3 and anything above that. So y is greater than or equal to -3, where y is a real number. Alright, now that we have some familiarity with standard form, let's work in reverse. We have information about the graph, and we want to come up with its standard form equation. So find the parabola in standard form that has a vertex of -3, 5. So I'm going to do a little sketch of this so I can understand it. Vertex here. It has an x-intercept of -1, so the graph passes through this point. Now, because of symmetry, we know that it would have to have another x-intercept an equal distance on the other side, there. So my graph looks something like so. So it opens downwards. Alright, so we're going to build the equation. It's really what we're being asked to do. What is the equation that represents that parabola? So the first thing to put in is the vertex, because the vertex is the values of p and q. Y equals a, x minus -3, which becomes +3, as we know, +5. Now we know that a is going to turn out to be a negative because the graph is opening down. But the issue is there's lots of graphs opening downwards from this vertex. Lots of graphs, right? It's wide ones, skinny ones, narrower ones. But we want the one that passes through these x-intercepts. Alright, so what we're told is that if the x-intercept is -1, the graph passes through -1, 0. And we know that if a graph passes through a point, that point must work in the equation of that relation. So if this point is on the graph, it has to work in this equation for x and y. So let's plug in y is 0, x is -1, and then we got to figure out what a would have to be to make that work. So this is 2 squared, that's 4a plus 5. Solving for a, -4a is 5, so therefore a is -5/4. And so we can complete the equation by putting that into that position. So our standard form equation is y equals -5/4, x plus 3 squared plus 5. So I've typed this into my calculator, a, x minus p squared plus q, and my graph should look like the sketch I had previously. Vertex of -3, 5, and it has an x-intercept of -1. So things are looking good.